Hello dear students, welcome to Wallah. So I hope you guys are doing well. So this is the one short series, and in this one short series today we will discuss about the fins and the critical radius of insulation. Right. So in fins what topics we will cover? In fins chapter what topics we will cover? Right. So first we will discuss about the governing equation for the fins. Right. What is a fin? Why fins are used? And what is the governing equation for the fins? Right. Then we will discuss about the infinitely long fin, right? Then short fin with insulated tip and short fin without insulated tip. Then we will discuss about the fin performance parameters, which is the effectiveness and the efficiency, right? And last we will discuss about the relation between the efficiency and the effectiveness. Okay. And in the critical radius of insulation, first we will discuss the concept of critical radius of insulation. Then we will see the critical radius of insulation for the cylinder, and after that we will see the critical radius of insulation for the sphere. Okay, so let's start today's session. So first we will discuss about the fins. What is the fin? What is the fins, and why there is a required of fins? Right. So let us assume there is a combustion chamber. Combustion chamber is there, and inside the combustion chamber, that combustion occurs. Right, inside the combustion chamber, combustion occurs. Right, and I want to increase the rate of heat loss. I want to increase the rate of heat loss from this combustion chamber to the ambient. Is it fine? I want to increase the rate of heat loss from this combustion chamber to ambient, right? So that this wall temperature should be maintained at TW. Is it fine? Right. And what is the temperature of the ambient? So let us assume I am considering the temperature of the ambient as T infinity, and the convective heat transfer coefficient, let us assume that is H. Right. So how this heat transfer will increase? What is the way by which we can increase this rate of heat transfer? Right, from the combustion chamber to the ambient. So as we all know that Newton's law of cooling, if I am talking about the Newton's law of cooling, so as per the Newton's law of cooling, because from the wall to the ambient, the mode of heat transfer is basically convection. We are neglecting the radiation right now here, right? So what is the mode of heat transfer? That mode of heat transfer is convection. So if you see the Newton's law of cooling, so as per the Newton's law of cooling, we can write now that is a HA TW minus T infinity. Right, HA TW minus T infinity. Is it fine? So what are the ways by which we can increase this rate of heat transfer? What are the ways by we can increase this rate of heat transfer? So what is the first way? That first way is by increasing the H. And how we increase this H? Right, we know that in free convection and the forced convection, that value of H will be differ, right? In forced convection, that value of H will be more as compared to the in free convection, right? And to get the forced convection, we need an external agent, correct? We need an external agent, and that external agent, let us assume that is a fan. So I am putting a fan here, so that the value of H should be increased, right? So this is the one way by which we can increase the rate of heat transfer, by increasing the H. Is it fine? By putting some external agent, right? So instead of the free convection, then forced convection occurs, right? And in forced convection, the rate of heat transfer will be increases, right? What is the another way? Right, another way is by decreasing the ambient temperature, right? By increasing the ambient temperature, so that this TW minus T infinity should be increased, right? So to increase the to decrease the ambient temperature, if your control volume, let us assume if there is a control volume, or let us assume if there if the ambient, if the surrounding is small, if the surrounding is small, let us assume this room is a surrounding, right? And there is some machine, and I want to increase the rate of heat transfer so that machine working properly, right? So I am doing here, what I am doing here, right? I want to decrease the T infinity, that means I want to decrease the room temperature. So if I want to decrease the room temperature, I am putting some ACs, right? I am putting some ACs. So because of that AC, because of that air conditioning unit, that T infinite, or I can say that ambient temperature decreases. If ambient temperature decreases, so TW minus T infinity increases. If TW minus T infinity increases, so rate of heat transfer increases. Is it fine? So this is the second way. Now what is the third way? Which is more popularly used? What is the third way which is more popularly used? Right? That is by increasing the area. Right? If I increase the area from where the heat transfer occurs, right? So definitely this rate of heat transfer will be increased. So there are three ways by which we can increase this rate of heat transfer. The first, by increasing the H. Second, by decreasing the T infinitive, so that TW minus T infinitive should increase. And third is by increasing the area. Is it fine? But now see, right? Now see this slide. Right, the heat transfer from a hot surface to the surrounding fluid takes place by convection, and it is governed by the Newton's law of cooling, as I already discussed. And as per the Newton's law of cooling, that Q dot is equal to HA Ts minus T infinity, right? So Q dot, this rate of heat transfer, is increased by either by increasing the convective heat transfer coefficient H, or by increasing the area of heat transferring surface or area, right? And third, by increasing the temperature difference, that is Ts minus T infinitive, by decreasing the T infinitive, right? Instead of the Ts, you can write Tw, no issue. Instead of Ts, you can write the Tw. Okay, Tw. Fine. Now see. Now, read this slide properly. It is not always possible. To increase the value of convective heat transfer coefficient H by increasing the velocity of flow, of fluid surrounding the hot surface, right? It is not always possible, right? It is possible, but it is not always possible. So, right, so let us assuming I am considering a case of transformer. Let us assume I am considering a case of transformer. You know, na, transformer. In the transformer, inside that heat generation occurs, right? And if I want to increase the loss of heat transfer, right? If I want to increase the rate of loss of heat transfer from the transformer to the ambient, right? So if transformer is at open space, then it is not possible. We are using fan there to increase the rate of heat transfer, right? It is possible at the some extent. If let us assume, if this is a room, and there is some device. Let us assume there is some device, and that device is continuously generating the heat energy. Let us assume some device, right? So if I want to increase the rate of heat transfer from that device, so that device should work properly, I'm increasing the H by putting a fan here, right? Or you take an example of your laptop, right? You should take example of laptop, right? In laptop, if you see, continuously heat generation occurs, na? And I want to increase the dissipation of the heat energy into the ambient, right? So what I'm providing, right? I'm providing a cooling pad, right? What is that cooling pad? That cooling pad consists a smaller fan, right? And that fan is used to increase the rate of heat transfer. So yes, in some cases, definitely we increase the convective heat transfer coefficient by providing a fans, or by increasing the velocity of the flow surrounding to that hot surface, right? But in some cases it is not possible, like a transformer, right? So it is not always possible to increase the value of convective heat transfer coefficient H by increasing the flow of the fluid surrounding the hot surface, or to increase the difference by lowering the temperature of the surrounding fluid which is in contact with the hot surface, right? That means I'm talking about the T infinitive. It is not always possible to decrease the T infinitive. Is it clear? Right. So what is more popular to increase the rate of heat transfer? That increase the area. Right. So basically the fins are the extended surfaces. Fins are the extended surfaces that is attached to the wall to increase the rate of heat transfer. Right. So if you provide the fins, then the area from where the heat transfer occurs increases. If area increases, then definitely the rate of heat transfer increases. So what is the fin? What is the fin? Fins are the extended surfaces. Fins are the extended surfaces that is attached to the wall to increase the rate of heat transfer. Right. So if you see here in this diagram, this is the bare surface. This is the bare surface. See, this is the bare surface. Bare surface means at this surface no fins are provided. At this surface no fins are provided. That is known as the bare surface, right? And this is the fin surface because fins are providing. See here, by providing these fins, these are the fins. These are the fins. So by providing the fins, that area increases. Which area? The area from where the heat transfer occurs. Is it fine? Okay. So there are some examples. There are some applications, I can say, application or examples of the fins. Right. So first see the cooling of the electronic components. Right. So cooling of the electronic components. Now see here. These are the fins. Extended surfaces. Right. In motorbikes. Right. In your bikes. This is the fin. Right. Another example. Transformer or machine or motor. Right. Electric motor. See. These are the fins, that extended surfaces. In transformer, see. Right. This is the fin. Right. So this is some application of the fins. These are the some application of the fins. Is it fine? Right. Now see. There are some type of fins. The first one is a straight fin. The first one is a straight fin of uniform cross section. The first fin is a straight fin of uniform cross section. See here, uniform cross section. Right. Now see. Uniform cross section. What is the meaning of that? Uniform cross section. Area is not changing with respect to x. Rectangular cross section. Area is not changing with respect to x. Is it clear? Now see the second one. This is a straight fin of non-uniform cross section. See. Non-uniform cross section. So area is changing with respect to x here. With respect to x here. A straight fin of non-uniform cross section. Right. Now see that third. This is the annular fin or you can say circular fin. Annular fin or you can say circular fin. Now see the next one. Now see the next one. This is the pin fin. What is a pin fin? That pin fin is basically a circular cross section fin. Pin fin is a circular cross section fin. So this is the non-prismatic, or I can say this is the non-uniform cross section pin fin. Prismatic means uniform cross section. Non-prismatic means non-uniform cross section. Right. So this fin is non-uniform cross section pin fin, or I can say non-prismatic pin fin. Right. There is a uniform pin fin also, uniform cross section pin fin also, uniform cross section pin fin also. Pin fin means circular cross section. So this is the uniform pin fin or uniform cross section pin fin. Right. So there are some types of fins. Okay. Now that most important is the analysis of the fins. That is the most important analysis of the fins. Right. So in analysis of the fins, right, what is our objective? So the first objective is derive the governing equation. First objective is derive the governing equation and find out the temperature variation. Right. In fin analysis, that first objective is derive the governing equation and find the temperature variation. Is it fine? And what is the second objective? The second objective is find the rate of heat transfer. Right. So for the analysis of the fin, I'm considering some assumptions. I'm considering some assumptions. And what are those assumptions? That first assumption is unidirectional. Okay? So this is unidirectional. That first assumption is unidirectional. Unidirectional, that means in one direction, and I'm considering that is a x direction. Okay, what is the second assumption? The second assumption is steady state is there. What is the third assumption? The third assumption is a uniform cross section. What is the fourth assumption? The fourth assumption is a constant thermal conductivity. Right. And what is the fifth assumption? That fifth assumption is there is no internal heat generation. Within the fin. And what is the next assumption? The next assumption is the radiation from the surface is negligible. That is our last assumption. The radiation from the surface is negligible. Okay, so this is the fin. Right, this is the fin. Right, so if you see here, this is the wall. If you see here, this is the wall. This is the wall. And what is the temperature of the wall? I'm assuming the temperature of the wall, TB. Right. And this is the x direction. I already assumed a unidirectional. And that is the x direction. So this is the x direction. Right. Now see, the length of this extended portion, or I can say the length of this fin is L. Length of the fin is L. Okay. And cross-sectional area is AC. The cross-sectional area is AC. AC is the cross-sectional area. Right. And this is the width. That is B. B is the width of the fin. Right. And let us assume that thickness of the fin is T. Is it clear? And air temperature is, outside air temperature is T infinitive and the convective heat transfer coefficient is H. Outside that air temperature is T infinitive and the convective heat transfer coefficient is H. Is it fine? Right. Now see, in analysis of the fins, basically we are doing the energy balance. Energy balance for what? Energy balance for this small element. So at a distance x, I am considering at a distance x, I am considering a small element of thickness dx, right? At a distance x, I am considering a small element of thickness dx, right? So this is the small element. See, this is the small element. This is the small element. Right, this is the small element. Is it fine? Right, and that thickness is dx. That thickness is dx. That thickness is dx. Right, so here, this direction is like this, na? Here, the direction is like this. The conduction heat transfer, that is a q dot x, I am assuming the conduction heat transfer from this small element is q dot x, and here it is q dot x plus dx. Q dot x plus dx. Right? Or you can say, just 1 minute, that is a q dot x. Q dot x, and the conduction heat transfer from this phase is q dot x plus dx. Q dot x plus dx. Right? So this is a conduction heat transfer within the fin, right? And see that outside, that means in the ambient, that rate of heat transfer, the mode of heat transfer, that mode of heat transfer is convection. So convection heat transfer from this small element is, this is the q dot convection. That is a q dot convection, right? So if you see this small element in 2D, if you see this small element in 2D, okay, so this is the wall temperature, or you can say base temperature, right? Now see, this is the fin, okay, and the length of the fin is L. Length of the fin is L. Length of the fin is L, right? And ambient temperature is T infinity, convective heat transfer coefficient, that is H. At a distance x, I am considering a small element. This is the small element, and what is the thickness of this small element? That is dx. Okay. So what is the rate of conduction heat transfer from this phase? What is the rate of conduction heat transfer from this phase? That is a q dot x. That is a q dot x. And what is the rate of conduction heat transfer from this phase? That is q dot x plus dx. Is it fine? Right. And in the ambient, the rate of heat transfer is via convection, so that is a q dot convection. Right? Now see here. I am assuming the thermal conductivity of the fin material is K. What is the K? The K is thermal conductivity of fin material. K is thermal conductivity of the fin material, right? What is the H? H is convective heat transfer coefficient. Convective heat transfer coefficient. Convective heat transfer coefficient, right? TB is the base temperature. Base temperature or Sometimes it is also known as root temperature, no? Base temperature or root temperature. That means temperature at x is equal to temperature at x is equal to 0. Temperature at x is equal to 0. Temperature at x is equal to 0. Fine. Okay. Now what is T? T is the temperature at any distance x. T is the temperature at any distance x. T is the temperature at any distance x. Okay, L is the length of the fin, right? L is the length of the fin. Length of the fin. L is the length of the fin. Fine. Now see, if you considering all these assumptions, right? If you considering all these assumptions, then I can say na that temperature is only function of x. Right? Temperature is only function of x, right? Because one dimensional is there. So there is no temperature variation in y direction and z direction, right? That steady state is there. That means temperature is not a function of time. So temperature is only function of space, and in the space the temperature is only function of the x, right? Temperature is only function of x. So I want to find out how the temperature is changing with respect to x. How the temperature is changing with respect to x, right? So for that we first write the governing equation. And governing equation from where we get the governing equation? So governing equation we will get from the energy balance only, right? Energy balance. So from the energy balance, from the small element, from energy balance, right? So now see, energy balance for this small element. So what is the energy balance? That energy balance is simply we can write that is a rate of heat or rate of energy in the small element is equal to rate of energy out from this small element. Rate of energy in is equal to rate of energy out. Simple, right? So rate of energy in, that is the q dot x. Now rate of energy out, what is the rate of energy out? That is q dot x plus dx plus q dot convection, right? Now see, AC, what is the AC? So I am considering AC as cross sectional area. I already discussed now what is the AC? That AC is cross sectional area. Okay. And what is the P? This P is perimeter of the fin. Perimeter, right? So if rectangular cross section is there, then you can find the perimeter, na? If P in fin is there, then you can find the perimeter, na? If P in fin is there, then pi d, right? And what is the cross section area? Pi by 4 d square. If rectangular fin is there, so what is the cross section area? That is b into t. And what is the perimeter? That is 2 into b plus t. That is the perimeter, right? So P is the perimeter and AC is the cross sectional area. Now see, if you solve this energy balance, then finally what you are getting, I write here the final expression, right? So if you are solving this energy balance, then what expression you are getting, right? What expression you are getting? You are getting this expression, that theta is equal to C1 e to the power mx plus C2 e to the power minus mx. C1 e to the power mx plus C2 e to the power minus mx, where theta is simply, it is t minus t infinitive. What is the theta? The theta is t minus t infinitive, right? C1 and C2 are the constant. Now see, what is the m? This m is root over hp by kc. Right? That is the m, right? C1 and C2 are constant. constant. C1 and C2 are constant. Is it clear? Right. So how we are getting this mathematical expression? How we are getting this mathematical expression? By solving the energy balance. So right now, solving the energy balance is not important. Right. Right now that solving this energy balance is not important. Right. But that energy balance should be clear. Energy balance should be clear. That's why I am starting from here. Right. So after the solving this energy balance, what is the Q dot X? Right. What is the Q dot X? That is the rate of conduction heat transfer, which is in. Right. What is the Q dot X plus dx? Rate of conduction heat transfer, which is out from the small element. What is the Q dot convection? That is the rate of convection heat transfer. We neglected the radiation heat transfer. So if you solve this energy balance, then this mathematical expression you will get. Is it clear? Right. So this energy balance is very, very important. This governing equation is very, very important. Is it clear? Is it clear? Okay. Now see here. C1 and C2 are the constant, and how this constant how we will find this constant? How we will find this constant? By using the boundary conditions. And boundary conditions are as per the type of fields. Right. So first I am talking about the infinitely long field. Infinitely long field. First I am talking about the infinitely long field. Infinitely long field. So everything is same. That up to the governing equation, everything is same. Right. What changes are there? Now to find out the C1 and C2, I am using the boundary conditions. Right. And what are those boundary conditions? So that first boundary condition is at x is equal to 0, we already know na, T is equal to TB. At x is equal to 0, the T is equal to TB, that base temperature, right? Or I can write at x is equal to 0, that theta is equal to theta B. At x is equal to 0, that theta is equal to theta B. And what is the theta B? That is TB minus T infinity. That is TB minus T infinity. What is the theta B? That theta B is TB minus T infinity. Is it clear? Right. By that theta is T minus T infinity. Na? Theta is T minus T infinity. So at x is equal to 0, T is TB. So this is TB minus T infinity. I am saying this TB minus T infinity is equal to theta B. So at x is equal to 0, because the solution of the governing equation, this is the solution of the governing equation. I think I already said it is a governing equation. No, this is a solution of the governing equation. Right, this is a solution of the governing equation. And if you want to see the governing equation is like this. Governing equation is d square theta by dx square minus m square theta is equal to 0. This is the governing equation. I'm sorry. This is the governing equation. And this is a solution of this governing equation. Is it clear? So this governing equation is same for infinitely long fin also. Right? And the solution of the governing equation, that is also same. Right. So theta is equal to C1 e to the power mx plus C2 e to the power minus mx. Now, so there are two boundary conditions are required. So that this is the first boundary condition. What is the second boundary condition? The second boundary condition is we are assuming that at x is equal to infinite, the t becomes t infinity. At x is equal to infinite, the t becomes t infinity. If t becomes t infinity, then I can say theta is equal to 0. Right. We are assuming that away from the base, temperature decreases. So definitely, right, temperature decreases. And at x is equal to infinite, we assume that the t reaches to t infinity. If t reaches to t infinity, that means theta is 0. Is it clear, na? Now see, here, this is the wall, this is the fin, right? This is the x direction, this is the x direction. Here the temperature is base temperature, and as we are moving in the x direction, the temperature decreases. Temperature decreases. So I'm assuming that at x is equal to infinite, that t becomes t infinite. T becomes t infinite. Okay? And in this case, the theta is equal to 0. Right. Now, if you are using these two boundary condition, then what you are getting? Right? You are getting the value of C1 and C2. So what is the value of C1, C? What is the solution? That theta is equal to C1 e to the power mx plus C2 e to the power minus mx. Right. Now see, at x is equal to 0, theta is equal to theta b. So this is theta b at x is equal to 0. So this is C1 plus C2. This is the one equation. This is the one equation. Now use the second boundary condition, right? And that second boundary condition is at x is equal to infinite. At x is equal to infinite, theta is equal to 0 now. Theta is equal to 0. So at x is equal to infinite, theta is equal to 0. See, this is C1 e to the power m infinite plus C2 e to the power minus m into infinite. Is it clear? Right. Now, e to the power minus infinite is equal to 0 now. E to the power minus infinite is equal to 0. So this term is vanish. This term is finish. Right. So ultimately what you are getting? You are getting C1 into e to the power infinite is equal to 0. And we know that e to the power infinite, this is not equal to 0. So ultimately what is 0? That C1 is equal to 0. See here. C1, if this term is vanish, then what you are getting? C1 into e to the power infinite. M into infinite is equal to infinite. Na? So C1 into e to the power infinite. But we know that e to the power infinite is not 0. Na? E to the power infinite is not equal to 0. So ultimately C1 is equal to 0. Right? So C1 is equal to 0. And from here you are getting, if C1 is equal to 0, that means C2 is equal to, right? C1 is equal to 0. So C2 is equal to, that is theta b. C2 is equal to, that is theta b. Right? Now, C1 is 0, C2 is theta b. Now put these two values or values of C1 and C2 in this mathematical expression. So ultimately what you are getting? From here, what you are getting? You are getting this. That is theta is equal to, this is theta b e to the power minus mx. Right? Theta is equal to theta b e to the power minus mx, or we can write theta by theta b. Theta by theta b is equal to e to the power minus mx. Right? Theta by theta b is equal to e to the power minus mx. Is it fine? Is it clear? Is it clear? Theta by theta b is equal to e to the power minus mx. Now see here, what is theta? That theta is, you can write in this way also, na? T minus T infinitive upon, that is Tb minus T infinitive is equal to e to the power minus mx. This one. Right. So from here it is clear that the temperature decreases with x, right? Temperature decreases with x, right? And that temperature decreases exponentially with x, right? We can say that temperature exponentially decreases with x. Is it clear? Right. So if you see the graph, right, if you see the graph between t and the x, so this is the T infinite. This temperature is T infinite. This temperature is T infinite, right? And at x is equal to 0, what is the temperature? At x is equal to 0, the temperature is equal to base temperature. At x is equal to 0, the temperature is equal to base temperature, right? And as x increases, see, as x increases, the temperature decreases exponentially. At x increases, the temperature decreases exponentially, right? So this is exponential. This is exponential decrement of temperature. Exponentially decreases. Exponentially decreases. Right? Temperature decreases exponentially with temperature. Okay, fine. Now see, so this is the first objective. How the temperature varies with respect to x. So temperature varies exponentially with respect to x. Now the second objective is find the rate of conduction heat transfer. The second objective is find the rate of conduction heat transfer. Second objective is find the rate of heat transfer through the fin. The rate of heat transfer through the fin. Second objective is rate of heat transfer through the fin. Rate of heat transfer from the fin. Rate of heat transfer from the fin. Right? So the rate of heat transfer from the fin we can write in this manner. This is equal to rate of conduction heat transfer at x is equal to 0. Rate of conduction heat transfer at x is equal to 0. Please try to understand this. If this is the wall, right, and fin is attached to this wall, right, and at x is equal to 0, what is the heat transfer, what is the mode of heat transfer at x is equal to 0? At x is equal to 0, what is the heat transfer from the fin? At x is equal to 0, what is the heat transfer from the fin? I can say at x is equal to 0, whatever the conduction is there, at x is equal to 0, whatever the conduction is here, the same heat energy, whatever the conduction is here, the same heat energy is equal to the convection heat transfer, right? And that convection heat transfer is nothing but the heat transfer from the fin only, right? So we can say right, whatever the conduction heat transfer that occurs at x is equal to 0, that is same as the rate of conduction heat transfer through the fin, right? So I am writing that thing only. At x is equal to 0, the rate of conduction heat transfer, we can find out this mathematical expression, Fourier law of heat conduction, and this is equal to the rate of heat transfer through the fin. Okay, now see, so q dot fin is equal to this is minus k AC dt by dx, minus k AC dt by dx at x is equal to 0. At x is equal to 0. Minus k AC dt by dx at x is equal to 0. Right? Now, we already know that t minus t infinitive upon tb minus t infinitive is equal to e to the power minus mx. So, t is equal to, that is t infinitive plus tb minus t infinitive, and that is e to the power minus mx. So what is dt by dx? That dt by dx is equal to tb minus t infinitive e to the power minus m e to the power minus mx. Right, now dt by dx at x is equal to 0, right? So at x is equal to 0, that is minus m Tb minus T infinitive, minus m Tb minus T infinitive. Is it fine? Now see, Q dot fin, the rate of heat transfer through the fin, that is equal to minus K AC, minus K AC, and that is minus m Tb minus T infinitive, and that is equal to KAC, and that m is root over HP by KAC. Or already told na what is the m is root over HP by KAC, and that is TB minus T infinitive, right? So ultimately what you are getting, that is root over, if you arrange this term, so this is HP by KAC into this is the K square AC square, and TB minus T infinity, you can say this is the theta, right? This is the theta. So that is equal to root over HP K AC theta B, and this is the rate of heat transfer through the fin. This is the rate of heat transfer through the fin. Okay, rate of heat transfer through the infinitely long fin, right? Infinitely long fin. So this is all about the infinitely long fin. Now come to the second type of fin. Come to the second type of fin, which is short fin. Which is short fin with insulated tip. Short fin with insulated tip. Short fin with insulated tip. So what is the meaning of the insulated tip? What is the meaning of the insulated tip? So if this is the wall and this is the fin, right, this is the wall, temperature TB, wall temperature is TB, right? And there is no heat transfer from the fin. What is the meaning of the insulated? Insulated means adiabatic. So no heat transfer from the fin tip, no heat transfer from here, no heat transfer from here, so that Q dot is 0, right? Outside temperature is T infinitive, convective heat transfer coefficient, that is H, and this is the x direction. This is the x direction. Thermal conductivity of the fin material, that is K. Right, so no heat transfer from the fin tip, that is known as the insulated tip, right? So governing equation is same, the solution of the governing equation is same, right? For this fin, the governing equation is same, na? Governing equation is same, d square theta by dx square minus m square theta is equal to 0, so this is the governing equation, right? And the solution of the governing equation is theta is equal to c1 e to the power mx plus c2 e to the power minus mx. c1 and c2 are constant which are obtained by the boundary conditions. And what are the boundary conditions here? Boundary conditions. So first boundary condition, is at x is equal to 0. At x is equal to 0, that T is equal to TB, and I can say theta is equal to theta B. At x is equal to 0, the T is equal to TB and theta is equal to theta B. So this is the first boundary condition. What is the second boundary condition? What is the second boundary condition? The second boundary condition is at x is equal to L. At x is equal to L, the rate of conduction heat transfer is equal to 0. Can I write? At x is equal to L, rate of conduction heat transfer, because the tip is adiabatic, na, insulated, na. So I write this mathematical expression at x is equal to L, the rate of conduction heat transfer is equal to 0. Rate of conduction heat transfer within the fin, that is equal to 0, and that is minus KAC dt by dx at x is equal to L is equal to 0. So ultimately what you are getting, the second boundary condition is this, dt by dx at x is equal to L is equal to 0. Right, so at x is equal to L, the dt by dx is equal to 0. So this is the second boundary condition. So if you consider these two boundary conditions, right, if you consider these two boundary conditions, then you are easily find out the C1 and C2. Right, you can easily find out the C1 and C2, and after finding the C1 and C2, what you are getting, that I directly write here, right? So that is theta by theta b is equal to theta by theta b, that is equal to, this is cos hyperbolic m L minus x upon cos hyperbolic ml upon cos hyperbolic ml, right? Theta by theta b is equal to cos hyperbolic m L minus x upon cos hyperbolic ml, right? So this is the temperature variation, with x, right? You can write this mathematical expression in this way also, no? This is T minus T infinitive upon TB minus T infinitive is equal to, this is cos hyperbolic m L minus x, cos hyperbolic m L minus x upon cos hyperbolic ml, right? So this is the temperature variation with respect to x. So here also the temperature changes with respect to x exponentially decreases. Here also temperature decreases exponentially. The temperature decreases exponentially, right? The cos hyperbolic x, you can write that cos hyperbolic x like e to the power x plus e to the power minus x by 2, right? So that temperature variation is exponential, and the temperature is exponentially decreases with x, right? So this is a temperature variation with x, right? Very, very important. Now second objective is, what is the second objective? What is the second objective? The second objective is, what is the second objective? The second objective is, what is the second objective? The second objective is rate of convection, what is the second objective? The second objective is rate of heat transfer through the fin. Rate of heat transfer through the fin. Rate of heat transfer. Rate of heat transfer through the fin. Rate of heat transfer through the fin. Rate of heat transfer through the fin. Right, what is the rate of heat transfer through the fin? So that is Q dot fin is equal to, this is minus KAC, again using the same concept, na? Using the same concept. And what is that concept? The concept is the rate of conduction heat transfer at x is equal to 0, that is equal to rate of heat transfer through the fin. Okay. So after differentiating it, what you are getting, what is the final expression for the rate of heat transfer through the fin? That I am writing directly. That is root over HPK AC. That is root over HPK AC theta B tan hyperbolic ml. The rate of heat transfer through the fin, that is root over HPK AC theta B tan hyperbolic ml. This is the rate of heat transfer through the fin. Okay, so this is all about the short fin. This is all about the short fin with insulated tip. Now, come to the third type of fin. That is a short fin without insulated tip. 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 Right. Now see. Again, governing equation same. The solution of the governing equation, that is also same. That only changes in boundary condition. So what are the boundary condition? Two boundary conditions are required. So first boundary condition. That first boundary condition is same. At x is equal to 0, that theta is equal to theta b. This is the first boundary condition. Right. And what is the second boundary condition? Now see here. The second boundary condition. See. At x is equal to L. At x is equal to L, that fin temperature is TL, ambient temperature is T infinitive, convective heat transfer coefficient is H, we already know, right? That at x is equal to L, the T is equal to TL. At x is equal to L, what is the temperature? That is TL, right? So this tip is non-insulated. That means the rate of heat transfer occurs from this tip. Rate of heat transfer occurs from this tip. Okay. So within the fin, if I say within the fin, the rate of heat transfer via conduction, and outside the fin, that means in the ambient, the rate of heat transfer that occurs through the convection. Right. Again I am repeating. At x is equal to L, inside the fin conduction heat transfer is there now. So rate of conduction heat transfer at x is equal to L, and the same rate of conduction heat transfer is going to outside now. That is via convection. So at x is equal to L, can I write the rate of conduction heat transfer is equal to rate of convection heat transfer? Can I write now? Right. So see, second boundary condition is at x is equal to L. At x is equal to L, the rate of conduction heat transfer, so already I wrote here at x is equal to L, so no need. So rate of conduction heat transfer is equal to rate of convection heat transfer. Okay. So what is the rate of conduction heat transfer? That is minus K AC dt by dx at x is equal to L is equal to, what is the rate of convection heat transfer? So the rate of convection heat transfer, that is H into AC into, that is TL minus T infinitive. So from where the convection occurs? The convection occurs from this surface only, na? From this only, right? So if you see. Okay, now see here. See, convection occurs from here only, na? Convection occurs here, right? So that is the cross section area, AC. From which area that convection occurs? This area is AC, na? This area is AC. So at x is equal to L, the rate of conduction heat transfer is equal to rate of convection heat transfer. So from here, AC cancel out from both sides. So dt by dx at x is equal to L. dt by dx at x is equal to L. That is equal to dt by dx at x is equal to L. That is equal to dt by dx at x is equal to L. That is equal to h TL minus T infinitive. H TL minus T infinitive. H TL minus T infinitive. H TL minus T infinitive by K. H TL minus T infinitive by K. and minus sign. So this is the second boundary condition, right? In the earlier case, at x is equal to L, dt by dx is 0, right? In this case, at x is equal to L, the dt by dx is minus h TL minus T infinity by k. So again, use these two boundary conditions. And by using these two boundary condition, you can easily find out the C1 and C2. And after finding the C1 and C2, put that C1 and C2 in this expression, where that expression, in this expression, and what you are getting, that is theta by theta b is equal to, that is cos hyperbolic m L minus x plus h by mk sin hyperbolic m L minus x. Fine. By cos hyperbolic ml plus h by mk sin hyperbolic ml. Right. So this is the temperature variation. Right. Okay. Now, what is the rate of heat transfer? Through the fin? So rate of heat transfer, using the same concept, rate of heat transfer from the fin. Use the same concept. Right? At x is equal to 0, rate of heat transfer through, at x is equal to 0, the rate of conduction heat transfer is equal to rate of heat transfer through the fin, right? So that q dot fin is equal to, that is root over HPKAC, theta b, and this is h by mk plus tan hyperbolic ml divided by 1 plus h by mk tan hyperbolic ml. Right? Root over HPKAC theta b h by mk tan hyperbolic ml plus 1 by h mk tan hyperbolic ml. Right? So this is the temperature, this is the rate of heat transfer through the fin, right? So it is difficult to remember these mathematical expression in this case, right? Short fin with insulated tip, easy, but short fin without insulated tip, little bit difficult to remember this mathematical expression, right? So if you want to remember this mathematical expression, then convert the short fin without insulated tip into short fin with insulated tip by using the corrected length. Right? So there is another mathematical expression. Also by using the concept of corrected length. So if you use the concept of corrected length, in the case number 3, short fin without insulated tip, then what you are getting? So that is T minus T infinitive upon TB minus T infinitive is equal to T minus T infinitive upon TB minus T infinitive, and that is equal to cos hyperbolic m L C minus x upon cos hyperbolic L C minus x upon cos hyperbolic ml upon cos hyperbolic ml. Okay, and what is the LC? What is the LC? That LC is, what is the LC? This LC is corrected length, corrected length. And similarly, you can find out the rate of heat transfer also, Q dot phi. And that is equal to root over HPKAC theta B, root over HPKAC theta B, tan hyperbolic MLC. Okay. So see, that remember the case number 2, insulated tip, insulated tip. You are getting the same mathematical expression. The only difference is instead of the LC, there you are using the L. Actually, L is the actual length of the fin, right? L is the actual length of the fin. And what is the LC? That LC is the corrected length of the fin. LC is the corrected length of the fin. And what is the LC? So this LC is corrected length. This LC is corrected length. And what is the corrected length? That corrected length is actual length plus S. Actual length plus S. And what is this S? This S is equal to cross-sectional area of the fin divided by perimeter of the fin. Cross-sectional area of the fin, cross-sectional area of the fin divided by perimeter, right? So if there is a pin fin, pin fin, that means circular cross-section fin. Pin fin, that means circular cross-section fin. So if there is a circular cross-section fin, then if there is a circular cross-section fin, that means the diameter of this pin fin is D. So what is a S? That S is equal to, this is AC divided by perimeter. And what is AC? That is pi by 4 D square divided by, that is pi D. Pi cancel out, D cancel out. So ultimately it is D by 4. It is D by 4. So what is S? That S is D by 4. In case of the pin fin, that S is equal to D by 4, right? And if there is a rectangular fin, then if there is a rectangular fin, then okay. Now see, this dimension I am taking as B, this dimension as I am taking as T, right? So in case of the rectangular fin, what is the S? So S is equal to cross-sectional area, that is B into T, divided by perimeter, so that is 2B plus T, right? And B is, if B is, or I can say if T is very, very small, actually fin thickness is small. If T is small as compared to B, then B plus T we can write, na, that is equal to B plus T is equal to B. B plus T is equal to B. B plus T is equal to B. So ultimately what you are getting, that S is equal to, this is B into T divided by, that is 2B. B cancel out, so S is equal to T by 2. Right. So in case of the rectangular fin, that S is equal to T by 2, whereas in case of the pin fin, that S is equal to D by 4. S is equal to D by 4. So is it clear what is the S? So first, what is the corrected length? The corrected length is L plus S. What is the L? L is the actual length. What is the S? That S is the corrected. S is the AC, right? AC cross section area divided by weight, cross sectional area divided by perimeter. Is it fine? Okay. Now come to the, but see, if you are using these mathematical expressions now, if you are using these mathematical expression, this mathematical expression, in case number 3, if you are using these mathematical expression and these mathematical expression, then you are getting the accurate result. Then you are getting the accurate result. But if you are using these mathematical expression, then these mathematical expression gives the approximate result. These mathematical expression gives the approximate result. But in GATE exam, you can use this mathematical expression also, because there is a range, right? And you are getting the almost same answer as you are using these mathematical expressions. Okay, so you remember the mathematical expression like this also, right? Now come to the next concept is Fein performance parameter. And there are two parameters, Fein performance parameter, Fein performance parameter, and there are two parameters. First one is efficiency. First one is the efficiency. If I say what is the efficiency of the Fein? What is the efficiency of the Fein? So efficiency of the Fein, this is equal to actual rate of heat transfer through the Fein. That means rate of heat transfer through the Fein divided by maximum rate of heat transfer through the Fein when the entire Fein surface temperature is maintained at the base temperature, which is a hypothetical thing. I am not saying this is a practical thing, right? See, if this is the wall, this is the Fein, okay, and I am considering another identical Fein. Okay, now see, base temperature is TB, outside temperature is T infinitive, material is thermal conductivity of the Fein material, that is K. So what is the rate of heat transfer here? So let us assume this is a infinitely long Fein. I am assuming this. So this is HPKAC theta B. Is it fine? But in this case, again I am considering this is an infinitely long Fein. But now see, this is a hypothetical Fein. Why it is a hypothetical Fein? Because here, everywhere the temperature, everywhere the temperature is equal to base temperature only, right? Outside temperature is T infinity, but in a Fein surface, everywhere the temperature is TB, which is a hypothetical thing, right? So how we will define the Fein efficiency? The Fein efficiency is, this is the actual rate of heat transfer through the Fein to maximum rate of heat transfer through the Fein when the entire Fein surface is maintained at base temperature. When the entire Fein surface is maintained at base temperature, right? So ultimately what you are getting, efficiency of the Fein, infinitely long Fein. I am taking an example of infinitely long Fein. So I write here, that is actual rate of heat transfer through the Fein, that is root over HP K AC theta B divided by what is the maximum rate of heat transfer? So that maximum rate of heat transfer, that is H into that is the surface area into TB minus T infinitive, right? So that is equal to root over This is the T, this is the theta B, this is also theta B, so cancel out. So HP KAC divided by H square. Now what is AS? Surface area. So surface area is perimeter into length. Na? Surface area is perimeter into length. Na? Perimeter into length. So that surface area is, you can write P square L square. H cancel out, P cancel out, and okay. So that is 1 by L, and that is root over, we can write in this way, this is 1 upon HP by KAC, and that is root over HP by KAC is equal to M, na? Root over HP by KAC, that is equal to M. So ultimately what you are getting, that is 1 upon ML. This is the efficiency of the infinitely long fin. This is the efficiency of the infinitely long fin, right? If there is a short fin, with insulated tip, then that is 1 by ml tan hyperbolic ml. This is the efficiency of the short fin insulated tip. If there is a short fin without insulated tip, so that is 1 upon ml, and that is tan hyperbolic MLC, tan hyperbolic MLC. Okay, is it clear? Is it clear? Right. So this is first fin performance parameter, which is the efficiency. Now come to the second fin performance parameter, which is effectiveness. Effectiveness. And that effectiveness is denoted by epsilon, effectiveness. So what is the effectiveness? What is the effectiveness? So that effectiveness is, see, if there is a fin, base temperature again TB, base temperature is TB, outside temperature T infinity, convective heat transfer coefficient is H, material thermal conductivity for the fin material, that is K. Fin material thermal conductivity, that is K. Okay. And this area, obviously this is a cross sectional area, na? This area, see, I am focusing on this area. Why I am focusing on this area? You can understand easily. This is the cross sectional area, which is AC. Right, the fin cross sectional area, that is AC, na? Right. Now see, what is fin effectiveness? So if that fin effectiveness is, this is the rate of heat transfer when fin is present to rate of heat transfer without fin. That means fin is not present. Right. This is the ratio of heat transfer with fin, rate of heat transfer with fin to rate of heat transfer without fin. If fin is there, then what is the rate of heat transfer? And if fin is not there, then what is the rate of heat transfer? The ratio, this ratio is the fin effectiveness. Now see, if fin is present, if let us assume I am considering this is the infinitely long fin. So if fin is present, then there is no issue. If fin is present, and I am assuming the infinitely long fin, the rate of heat transfer through the fin is root over HP KAC by theta B. Right. If fin is not present, if let us assume this fin is not present, then what is the rate of heat transfer from this portion? Because fin is fitted here, na? Fin is fitted here. So what is the rate of heat transfer from this area? So that is simply I can say this is Q dot without fin. If fin is not present, then what is the rate of heat transfer? That is equal to H into AC into TB minus T infinity. Right. From here to, from this wall to ambient, what is the rate of, what is the mode of heat transfer? That is convection. Right. And what is the area? from where the convection occurs, that is the AC. What is the convective heat transfer coefficient, that is H. What is the base temperature, TB, and what is the ambient temperature, that is T infinity. So rate of heat transfer without fin, that is HAC, and this is TB minus T infinity, TB minus T infinity, right? So ultimately what you are getting, that effectiveness is equal to, right? So again, this theta B and this TB minus T infinity is eliminated, cancel out. Okay, now effectiveness, so I am considering a case of infinitely long fin. So effectiveness in case of the infinitely long fin, that is root over HP KAC, that is root over HP KAC divided by H square AC square, H square AC square H. So ultimately that is equal to root over PK by HAC, and this is the effectiveness, of the infinitely long fin. This is the effectiveness of the infinitely long fin. Is it fine? Is it fine? Right. And similarly, effectiveness for short fin with insulated tip, that is equal to effectiveness short fin with insulated tip, that is equal to short fin with insulated tip, that is equal to root over PK by HAC tan hyperbolic ml, tan hyperbolic ml. If there is a short fin without insulated tip, short fin without insulated tip, short fin without insulated tip, then I'm sorry na, root over PK by HAC, root over PK by HAC tan hyperbolic MLC, tan hyperbolic MLC. So this is the effectiveness of the short fin without insulated tip, this is the effectiveness of short fin with insulated tip, and this is the effectiveness of infinitely long fin. Okay. Okay, now that effectiveness of the fin, how we will increase the effectiveness of the fin? How we will increase the effectiveness of fin? Because apply the fin, fin, apply the fin is justified when the effectiveness is greater than or equal to 2. Please try to understand the things. That putting a fin is justified when the effectiveness is greater than or equal to 2. Greater than or equal to 2. Right? Or I can say apply the fin is justified when the effectiveness is greater than or equal to 2. Right? If effectiveness is, let us assume that effectiveness is less than 2, then that applying the fin is not justified. Applying the fin is not justified because ultimately the rate of heat transfer not much increases. If let us assume I am considering that effectiveness is equal to, let us assume that is 1.2. Effectiveness is equal to 1.2, right? So if you are putting the fin, then the rate of heat transfer with fin is equal to 1.2 times of the rate of heat transfer without fin. Is it fine? Right? So when you are putting a fin, then the rate of heat transfer through the fin is 1.2 times of rate of heat transfer without fin. Right? So that heat transfer is not much increases, but when you apply the fins, then the cost of the fin is high. Cost of the fin is high. So that is not justified. That rate of heat transfer increases little bit, but you are applying a fee, you are increasing the cost. Is that fine? So use of the fiends is only justified when the effectiveness is greater than or equal to 2, right? So what are the ways, by which we can increase the effectiveness of the fiend? What are the ways, right? So that first way, see here, that mathematical expression you have, that effectiveness is equal to, that is root over pk by HAC, right? So what are the ways by which we can increase the effectiveness? So effectiveness is increased by A, by increasing the thermal conductivity. That means we are using a material for the fiend having the higher thermal conductivity, right? We are using a material, we are using the fiend material having higher thermal conductivity, right? Like that most commonly used fiend materials are aluminium alloys, copper alloys. These are the most frequently used fiend materials, right? So if you increase the thermal conductivity, then the effectiveness of the fiend will increase, right? What is the second way? By increasing this ratio, that is P by AC, by increasing this ratio P by AC, right? Perimeter to cross sectional area, right? So by increasing this P by AC, that effectiveness increases, right? Or this statement we can say in another way also, right? See here, if I am considering, let us assume I am considering a rectangular fiend. So rectangular fiend, width is B, thickness is T, length is L, thermal conductivity is K. Now what is P by AC? Now P by AC is perimeter. Perimeter is 2B plus T. And what is the cross sectional area? That is B into T. If B plus T is approximately equal to B, that means thickness is very, very small, then I can say this is, right, this is 2 by T. No? This is 2 by T because B plus T is approximately equal to B. B cancel out. So this is 2 by T. Right. So I want to increase this P by AC ratio. Na? P by AC ratio should be more. So T should be less. Na? Thickness should be less. Right. If thickness is less, then P by AC will be more. Right. So either I can say that P by AC increases. To increase the effectiveness, P by AC ratio increases, or I can say the thickness decreases. Right? And that is a reason we are using thin fiends. Thin fiends are more effective. As compared to the thick fiends. Right? Thin fiends plus closely spaced. Right? So thin fiends are more effective as compared to the thick film. What is the third way? The third way is by decreasing the H. If H decreases, then that effectiveness increases. H decreases, then effectiveness increases, right? So if I am asking one question, let us assume there is a combustion chamber. And in this side air is a medium, and in this side water is a medium, right? So there is a combustion chamber, and I want to remove the heat from this combustion chamber. I want to dissipate more and more energy. I want to dissipate more and more heat energy from this combustion chamber, right? So in which side I am putting a fiend? Because I want to increase the rate of heat transfer. I want to increase the heat energy dissipation. So which side I am putting a fiend? Air side or water side? Which side? So answer is put the fin on air side. Put the fin on air side. Why on the air side? Because air side, that convective heat transfer coefficient is less as compared to the convective heat transfer coefficient water side, right? That water side, the convective heat transfer coefficient is more, H is more. Whereas in the air side, the convective heat transfer coefficient is less, right? So H air side is lesser than the H water side. That's why we are putting the fin on the air side, not the water side, because water side already the heat transfer occurs in a good amount. In the water side already the heat transfer occurs in a good amount because that convective heat transfer coefficient of the water side is more. But in the air side, the convective heat transfer, in the air side that heat transfer not occurs in a in the air side that heat transfer not occurs in a good amount. So if you are putting the fin, then definitely that heat transfer rate increases on the air side. Is it clear? Right. And that's why I can say that effectiveness is increases by decreasing the H. Okay. So I hope it is clear to everyone. Okay. Now come to the last topic. And the last topic, not actually, that is not a topic, that is a concept. See here. Q dot fin divided by Q dot without fin. Now see here, this is basically effectiveness. And this Q dot fin, I can write this Q dot fin in this way now. If I am taking an example of the infinitely long fin again, so this is a Q dot fin. So this is minus KAC dt by dx at x is equal to 0. We can write in this way now. I already discussed. Right. In case of the infinitely long fin, the dt by dx, so this is minus KAC. So t is equal to this is t infinity plus this is theta b, and this is e to the power minus mx. Okay, fine. So what is dt by dx at x is equal to 0? So this is theta b minus m, right? So now put here minus m, and this is theta b. So I can say this is KAC m theta b, right? This is the rate of heat transfer with fin. And I am assuming infinitely long fin here. To understand this concept, I am assuming infinitely long fin, right? Now see, if fin is not present, Q dot without fin. So already discussed, that is equal to H into AC theta b. Fine. Now see here, this is equal to K AC m theta b divided by H AC theta b. Theta b cancel out, right? Now AC cancel out. So ultimately this is mk by H. This is equal to Q dot fin upon Q dot without fin. Now from here we can form three cases. What are these three cases? That first case, when H is equal to mk, right? If that value of H is equal to the product of m into k, and what is the m? That is the root over Hp by Kc. So that value of H is equal to product of m into k. So in this case, the rate of heat transfer with fin is equal to rate of heat transfer without fin. So tell me guys, in this case, there is a need of a fin? No, there is no need of fin, because if you are providing the fin, and if you are not providing the fin, the rate of heat transfer will be same. Then what is the need of the fin? That only cost will be increases. The heat transfer rate not increases. So in this case, no need of the fin. No need of the fin. In this case, no need of the fin. There is no need of the fin, right? Second case, when H is greater than mk. When H is greater than mk, that means I can say mk is lesser than H. That means this ratio is less than 1. If this ratio is less than 1, then Q dot phen is lesser than the Q dot without phen. That means if you are providing the phen, the rate of heat transfer decreases. If you are providing the phen, the rate of heat transfer decreases. When you are not providing the phen, the rate of heat transfer is more. But if you are providing the phen, the rate of heat transfer decreases when that H is greater than M into K. In this case, that phen material itself is acting like a insulating material. That phen is act like, in this case, the phen itself act like as insulator or insulating material. And that's why there is, okay, if you're providing the phen in this case, the rate of heat transfer decreases. Okay. Now, case number 3. When H is lesser than Mk, when H is lesser than Mk, or I can say Mk is greater than H, and only in this case, rate of heat transfer with phen is greater than the rate of heat transfer without phen, and in this case, you apply the phen, because in this case, when you apply the phen, rate of heat transfer increases. So when H is less than Mk, when H is less than Mk, and in this case you are applying a phen, then the rate of heat transfer definitely increases as compared to without phen. Is it clear? So I hope this phen topic is clear to everyone. Okay, so this is all about the phen. So basically in phens, we studied about the energy balance. We studied about the first we studied about the what is a phen, why there is a need of a phen, right? Then energy equation, right? Then energy equation, and by using that energy equation, we derive the governing equation, right? And by energy balance, we derive the governing equation and the solution of the governing equation, right? After that, we are discussing about the 3 cases: infinitely long phen, short phen with insulated tip, and the short phen without insulated tip. Then we discuss about the phen performance parameters, right? And in phen performance parameter, effectiveness and the efficiency. There is a last topic, relation between effectiveness and the efficiency. Sorry, I forget this topic. Relationship between effectiveness and the efficiency. Relationship between effectiveness and the efficiency. What is the relationship? So you can easily find out, na? You know the effectiveness formula. Let us assume I am considering for the infinitely long phen. So you know the effectiveness formula, you know the efficiency formula, right? Just divide it, effectiveness and efficiency, divide it. So ultimately what you are getting this. You are getting this, surface area to cross-sectional area. Surface area to cross-sectional area. Surface area to cross-sectional area. So what is the ratio? What is the ratio of effectiveness and the efficiency? So the ratio of effectiveness and the efficiency is equal to surface area to cross-sectional area. Is it clear? Right. So effectiveness, efficiency, what is the relation between the effectiveness and the efficiency, and how the effectiveness of the phen is increased, right? What are the ways by which we can increase the effectiveness of the phen? So this is all about the phens. Is it okay? Okay.